Hello students, in this video I'm going to talk about the second half of section 5.2, which is probability basic stuff. The good news is you already did the hard stuff in the first section. This one's going to be covering what's called the addition rule, which is a little bit more intuitive than the multiplication rule that we covered last time, and then we're also going to be talking about how to use some visuals to make life easier for us, including two-way tables and Venn diagrams. Later on there's going to come trees, but that's in the future. For now we're just going to wrap the section up, hopefully fairly quickly. I look forward to getting yelled at if I don't do this quickly. So we already talked about the notion of independence between two events. And I think I briefly talked about exclusivity too, which is to say that if I have two events A and B, the overlap between them is non-existent. It's impossible for A and B to occur at the same time. What's the converse of that? Like, what are two things that are not mutually exclusive? We'll talk about that in a bit. But for starters, let's look at things that obviously are mutually exclusive, like the probability of, when I roll a die, I either get a 2 or a number that's greater than 4. Well, there is no number that is equal to 2 and also greater than 4 at the same time, so we say that these events are mutually exclusive. You probably don't need the formula for this because it's pretty intuitive, that what I could do is just look at the probability that the first thing occurs, look at the probability that the second thing occurs, and then add those two numbers together. It is that easy. On a 6-sided die, one of the faces is a 2, and two of the faces, 5 and 6, are greater than 4. So 1 6 plus 2 6 is 3 6, which is 1/2. Easy. Those of you that aren't familiar with decks of cards, I have it on the last page for reference, but it's this bad boy where there's 52 cards. You can kind of see that there's a fourth of that whole deck is a suit, and then half is black and half is red. So when I say find the probability that I have a red card or a spade, which, by the way, if you're not a gambler, spades are this top one right here, which is not red at all. We see that there is no overlap between this. There is no red spades. So if I want to know the probability that I pull a red card or a spade, I look at the probability that the card I pull is red, which is 1/2. I could write this out of 52 if I wanted to, but it's easier to just look at it in terms of the proportions of the whole. And again, one of the 4 suits is spades. So there's a 3/4 probability that if I pull a random card from the deck, it's going to be a red card or a spade. The remaining 1/4 of this that's not is clubs. Clubs are not red, and they're not spades. So that accounts for the complement of this. Another thing that is, another set of things that are mutually exclusive events are ending up with any one of these blood types. Everybody has one blood type. So if I have a group of 20 students, I know that each of those 20 students has one singular non-overlapping blood type. Let's say in this case that 5 of them are type O, 9 are type A. 4 are B, and 2 are AB. So if I pick a random student and I want to know the probability that it's a type O or type A, this is relevant because O is the universal donor, so if I need to donate to someone with type A blood, this is the subset of people who I want to be pulling blood from. If I want to know what proportion of the 20 students are O or A, or the probability that a rando is one of those things, it's the 5/20ths that are type O, and the 9/20ths that are type A. You add them up, you get 14 out of 20. 0.7. Bing, bang, boom. Easy peasy. So now when it's not so easy peasy is if I talk about when there's overlapping events, which is not mutually exclusive, which is inclusive. Take a second to not even read this page for a minute. Just close your eyes and think. If I were to ask our class, if I want to know the probability that if I pick a random student in our class, it's going to be a girl or somebody with blonde hair, and I say, okay, everyone who's a girl, raise your hand, and then they do. And I say, everyone who's a blonde, raise your hand, and they do. And then I add up those two numbers and divide by the total number of students. That probably seems like a fine way to do it to most people, except for the blonde girls, because the blonde girls are the overlap, and they've been counted twice. So what do we do to undouble count the overlap? We subtract it. So we say the probability of A or B is the probability of A plus the probability of B minus those that we've double counted, which is the overlap between those two things. In the Venn diagram, that's the visual representation of that overlap. So, yes, this is a formula. Normally it would be something that you might think you have to remember, but no worries. It's one of 2 formulas on our reference sheet that relate to this chapter. Remember that this union thing really means or. This upside down U symbol is and. So when I say find the probability of A or B, I'm really saying find prob A plus prob B minus the probability of A and B. Like in the situation I just talked about, I would subtract the proportion of blonde girls in the class because that makes it so that they're only counted one of these categories instead of both. So if I compare this formula to what we just talked about in the last page, it's more or less the same except for the overlap bit at the end, the minus P of A and B bit. But keep in mind that if two things are mutually exclusive, then the probability of A and B is 0. This bit is 0. So it's not even like it's two different formulas. It's just that this highlighted part doesn't apply when A and B are mutually exclusive events. So it's just one less thing to have to worry about. This formula applies in both situations. It's just that when they're mutually exclusive, it's a little bit more simplified. We just add, we don't have to worry about subtracting an overlap, because by definition, if they're mutually exclusive, there is no overlap. So back to this. Fine, here we are. Again, if you're not a card person, you could always flip to the last page in the notes templates to try to figure this out. But if I pick from a deck, if I want to know the probability that I select a queen or a diamond, I could add the probability of getting a queen. Queen is 1 out of 13 face cards. I could add the probability of getting a diamond, that's a quarter of the cards. But then the overlap in this case is the queen of diamonds. There's one overlap. So if I take my 4 queens out of 52, my 13 diamonds out of 52, and I subtract the 1 overlap, the queen of diamonds out of 52, then I end up with a 31% chance. Cool. Easy peasy. When I roll a single die, find the probability that's an odd number or it's greater than 3. Well, we want to subtract the probability of rolling an odd number that is greater than 3 because that counts as A and B. So 3 of the numbers are odd, 3 of the numbers are greater than 3, 4, 5, 6, right? And I'm subtracting the overlap because a number that's odd and greater than 3 is 5. So I end up with the probability of 5/6, which if you think about it is just every number except 2, right? Whoops. So university journalism class of 80 seniors and 70 juniors was polled about whether or not they read the news. Of the 130 who said yes, 68 were juniors. If a student is chosen at random, find the probability he or she is a senior or reads the paper. Fine. This one actually requires a little bit more brain power than the rest, so I recommend maybe pausing it and stopping to think for a minute. If you caught my screw up right there, what I did was I started with the formula, and then I sort of plugged in the stuff that I recognized that it either gives me or that I could deduce from there. And then it kind of just became a matter of simplifying. But thinking through the values of these things and kind of weeding through the words is a tricky thing. So if you want to pause it, go for it. But I'm going to go ahead and blast ahead here. I think the only thing that's not immediately obvious to us is the probability of selecting someone who's a senior and reads. So what we should acknowledge is that there are 150 students, 80 are seniors, 130 are readers. If I just add those two things up alone, that's already 210 out of 150, which is more than 100%. That should indicate that there's a problem in our method if we don't remember to subtract the overlap. So how do we know the overlap is 62 seniors who read? Well, we're told 130 of the 150 said yes, they read, and 68 of them are juniors. Well, the complement of that would have to be the other 62 students who said yes, who have to be seniors. So if we do that math, we end up with 148 out of 150, which is everyone but 2 students. So if we think about who those 2 students could be, anyone who's not a senior or a reader is a junior who doesn't read. So note that out of the 70 juniors, 68 of them said yes, they do read. So the remaining 2 out of 150 is the remaining 2 juniors who don't read. FYI, not that it asked, but it's always good to think through this logically and make sure our answer makes sense, which it does, of course. This is kind of a callback to Chapter 1 when we were dealing with two-way tables. I think we did a bit of probability stuff with this, but most of the potential difficulty here is just knowing how to read what it's asking for and making sure we're giving it to them. So if I have a case like this where I say 310 high school students are surveyed regarding whether or not they have at least one ear piercing, and the following table categorizes their response by their sex. So if I want to find the probability that if I select a random person from this study, what's the probability that they have their ear pierced? So we kind of need to know, and if you haven't taken a moment yet to digest this table, think it through, it's a good way of representing two categorical data pieces. I guess I should say sex instead of gender, but one is gender and the other is pierced status, or sex rather, and the other is pierced status. So this breaks us up into our 4 potential categories here, yada, yada, yada. If I say what's the probability that they have pierced ears, we know the total number of people with pierced ears is 152, and the total number of people from whom we are randomly selecting is 310. Not bad. If I want to know the probability that the person is a male with pierced ears, which we could read as male and pierced if we look at those two events as an A and B situation. Well, there's the one box that indicates this. It's 32, And again, our sample space from whom we are selecting is the 310. So we do that math, we get like 10 and change percent. And again, it's okay to represent either of these as a percent or a decimal or a fraction, whatever makes you happy. Just make sure that you're rounding to a reasonable number of places. I'm kind of hopping back and forth between rounding to 3 and 4 places. So something like that, whatever makes you happy. If I say I want to find the probability that this random person is a male or has pierced ears, well, if we have a visual like this, we can sort of use that to our advantage to just keep in mind, or more or less highlight who from our sample space fits this criteria. This person's a male or has pierced ears. This person's not a male but has pierced ears, so they satisfy this blue criteria. This person, or I should say these 118 people are male, and though they don't have pierced ears, they satisfy the first part of the or statement. So we're good. What I could do is I could add these up and divide by 310, or if it makes you happy, we can just go straight to the formula that we've been talking about on the previous page. I think using the sample space to our advantage and just accounting for what satisfies our events is an easier way to do it, but I know formulas are, they're comfortable for people. They make them happy because they always work. You can always plug stuff in. So what proportion of the people are male? It's 150 out of 310. That's where that comes from. What proportion of people have pierced ears? That's 152 out of 310. That was from the first question even. What's the overlap? Well, the overlap is A and B, male and pierced ears. So we can subtract them because they've been counted. These 32 people have been counted amongst the 150 and the 152. So to go back from double counting to single counting, we subtract them. We get something like 87.1%. Fine. So this next thing, and I hope you're paying attention because I promise you some people are going to make this mistake on a quest or something. But if we say, why isn't it the case that if I just multiply these two things, let me back up and say, if I want to find the probability of someone who's a male and pierced ears, why not just take the probability that they're male times the probability that they have pierced ears? We've been doing the whole multiplication thing before. Why not now? Why doesn't it work now? Because if you actually do multiply these two numbers, you get something like, hang on a minute, like 24%, which is not the answer here. So why not? Well, remember that this multiplication rule only works when the two variables are independent. And if I ask you, is somebody's sex and their pierced ear status independent, you would say absolutely not, because, let me clear out all the mess here. Look, we could actually see that males are considerably less likely to have pierced ears than females, which indicates that somebody's sex is not independent of their ear pierced status at all. So the multiplication rule doesn't apply. Later on, we'll talk about conditional probability, but for now, just know not to overextend our applications here, and that independence is something that we should consider in the back of our mind. Just use the visual. Really, I think that's the bottom line of this whole page. Really just use the table and kind of like pick and choose things that fit our criteria to make life a little bit easier for us. For the most part, like everything else on this is just practice. So I'd recommend like pausing and trying and maybe kind of fast forwarding through the video and looking for answers. But I'm going to persist anyway, just for those that want to like use this for reference. At a high school of 1,400, suppose 550 students take French, 700 take Algebra 2, 400 take both classes, students chosen at random. So if I want to find the probability that the student chosen at random is taking Algebra 2 or French, I can simply add the probability that they're in Algebra 2, add the probability that they're in French, and then subtract the overlap. All of these numbers are generously given to us, so we don't have to work too hard to get our answers here. Same thing with the next one, where if I kind of add these probabilities individually and then subtract the overlap, we get our answer. However, post-graduation plans, if we're talking immediately anyway, are mutually exclusive. At least we're saying that that's the case here. I know there's some like ROTC plans. I don't know if that counts exactly, but whatever. We're going to say you either go to university, join the workforce, enlist, or other. So there is no overlap between these things. All these numbers add up to 400, which tells us that there is no overlap. No one has been double counted because our sum is equal to the total number of people that we would expect. So cool. Great. This next one, number 3, is a little bit tricky. And notice that for 1 and 2, we're looking for A or B sort of situations. This is A and B. But we can still use our formula. Now we're just solving for a different ingredient, though, because remember, I essentially have 4 different kind of terms, 4 different probabilities that I'm dealing with, and if I know any 3 of them, then I could find the 4th. So let's look at what we do have. We know that everybody has a dog or cat. No children have neither pet, which means that all 30 out of 30 are accounted for as being dog or cat owners. So we know that 19 own a dog, 17 own a cat, and we don't know the overlap, but we know it exists because it has to. Why does it have to exist? Because this sum right here is 36, and we know there's only 30 kids in the class, which means we've now double counted 6 students. That tells us that 6 out of the 30 own a dog and a cat, which means that a fifth of the class owns a dog and a cat. Whew. One more question, and I'm going to go through this one anyway because we haven't yet really talked about how to utilize a Venn diagram from scratch. We've looked at how it's a good tool for helping us understand the whole exclusivity thing, or lack thereof. But I think actually using one to generate an answer is a valuable skill too. So I'm going to go through this question. Again, I recommend pausing and trying, but here I go. Last Saturday at, Pasquale's Pizzas and Wings, 60 customers were served over the course of the evening. 52 customers ordered pizza, 16 with buffalo wings, 12 ordered both. Suppose we select a customer from last Saturday at random. If I fill in the diagram here, an important thing too as far as showing work, if we're going to be answering some of these on like an FRQ, is if they don't give us a variable for these, we're going to assign some variables. And I'm choosing ones that make sense. P for pizza, W for wings. And we know there's going to be some overlap here because it tells us 12 customers ordered both pizza and wings. So let's start from that. Let's also acknowledge, and if you're wondering where this 40 and this 4 came from, if you're going into this problem now without having tried it on your own first, take a moment to think and recognize that the 52 customers who ordered pizza, that includes those who didn't get wings on just the red side here and those who did in the purple. So what we know is that this whole pizza bubble should add up to 52. And if we know the overlap part is 12, then the other 40 must be ones who only ordered pizza. Thus, they fall into this section. Same thing here with the wings. We know that 16 people ordered wings. That includes not just the only wings section, but the wings and pizza section. So if I know that this whole blue bubble has to total 16, and if I know that the overlap is 12 of the 16, then the remaining 4 have to just be wing people. So we haven't actually been asked the question yet, but being able to boil it down to just pizza, just wings, both, and then neither, that's really important for being able to answer whatever question is going to be coming our way shortly. And just like on the previous page, we could apply a formula here too if that makes us happy. But again, I feel like a visual is important. So noting that 40 and 12 and 4 is 56 people, 56 customers, and there were 60 total. The difference of that is 4, which means that if 56 falls in one of these two bubbles, or both, then the remaining 4 have to fall outside of it. This 4 is the neither pizza nor wings group. Who knows what else they ordered at a pizza place. It's called Pascal's Pizza and Wings. What are you doing for, people? Anyway, what's the probability that a randomly chosen customer did not order wings or pizza? Justify your answer with appropriate calculations. So we just did. I just railed against those 4 people. No wings and no pizza, and I could do like fancy complimentary things here with W and C and P and C. But you get it. Words are sufficient here that there's now a 1 out of 15 chance that if I randomly select a customer out of the 60 from this evening, they're going to be someone who ordered neither of these two things. So I showed the work here on the side. Even filling out a Venn diagram without my little side work here is sufficient work shown considered for an FRQ. So take a minute to digest this. Note that it's going to take a bit of practice to get good, and you're not expected to be amazing right now. That'll come with time. Thanks for watching.